Hi, everyone. Welcome. I'm glad that you could join us. Today's speaker is Hao Hao Tan, who's a research assistant at SUTD. Hao Hao received his Bachelor of Engineering Computer Science at NTU, and he's been at SUTD now for, I think, 1 or 2 years. And Hao Hao is currently working on music generation based on video content and perceived emotion. Hao Hao, whenever you're ready.
Sure, thanks a lot, Dorian. First of all, just to check, can everyone hear me in the group? Can everyone hear me?
I can.
Okay, cool. Thanks a lot. Yeah, thanks a lot. Yeah, the chat is cool. The chat is fine. Thanks a lot. So yeah, this will be a good one. So if anyone has any questions in the middle of this presentation, feel free to put it in the chat. If I can, I will address it immediately, or else I'll definitely address them after the presentation. Okay, so let's start. Thanks, Dorian, for giving me such a good introduction. And first of all, thanks so much for joining today's webinar. And I hope every one of you guys stay safe and sound wherever you are in these epic timings. Yeah, so today's presentation will be on style-based music modeling with latent variable models. So today I use the term music modeling because it will be more generic, because when you have a good music model, you can use it for either generation tasks, synthesis tasks, analysis tasks, and so on. So okay. So the outline today, for the first three parts, I will give more of a prerequisite knowledge for how we can understand latent variable models and some of the important parts such as disentanglement, controllability within these architectures. I will also talk about strengths of latent variable models for style-based music modeling. I'll talk about some controllability techniques that we can use in latent spaces. Then after we understand all of this, I will put it into a context within two of my works to see how we can use all of these techniques in place. One of it is on audio synthesis for piano performance, and the other is to learn to control high-level qualities via low-level features. Yeah, let's start from the introduction. So we use the term style in today's title. So what is actually style? In this music style transfer paper, they claim that we don't really have a well-defined concept, and it is really a fuzzy term that can refer to any aspects of music. So if we look at this list here, there are many ways that we can interpret and classify the terms of style, right? From acoustic features such as timbre, from compositional features such as rhythm, note, harmony, all those score level features. We also can have performance level features such as articulation, tempo, and so on. We also have high level semantic features such as emotion, mood, tension, which are often more abstract. So one thing I need to take note is that when we are looking at this list, we actually can find some kind of hierarchical structure, or we can say that it is arranged in a more low level to high level way, where for acoustic features, like sound features, it is more low level. The compositional features and performance features are more mid level, and it goes to a more abstract and high level features when we talk about motion and mood. Yeah, so in terms of music modeling, style actually refers to anything where it is often a parametric musical feature that we wish to explicitly model and control. So the second term that I want to give an introduction is latent variable models. Excuse me. So if you guys don't know, last week we actually have a brilliant presentation by one of our colleagues, by my senior Yin Jun Law. So he actually gave a very detailed explanation on this. So if you guys have any questions, feel free to refer to that presentation. And the frameworks that I'm covering today are actually highly overlapped with what he has introduced. So I will go through this part in a more faster manner. Yeah. So in simple terms, latent variable models basically means models that relate observable variables with latent variables. And we can use this equation to manifest this relation. It's basically that tells us that how we generate a point X is that we first sample it from a prior distribution, Pz, which prior distribution simply means how you assume your latent variable distribution looks like. Yeah. And after we have the latent variable, we infer the data point by itself from the given latent variable. And often in this type of models, we're interested in inference. Inference in simple terms means that you're inferring the latent variable given the observation, and it can be manifest in this form. And in the last week's presentation, we also covered a problem, which is the intractability of posterior, which is this term, which is hard to calculate for all kinds of reasons, and it's often been approximated using variational inference. So in my work, I actually use a lot of variational autoencoder as well, thanks to June. So because the variational inference process can be formulated as an autoencoding process. So this is the idea of variational autoencoders. Then after a lot of processing, a lot of derivation, you can always get an elbow function from this a variational autoencoder, which can be divided into two terms. The first one is the reconstruction term, and the second one is the regularization term, which you regularize the latent space to conform to a prior distribution that you want, which is often a standard Gaussian. Okay. And of course, we can extend this prior into Gaussian mixture. We don't want the latent variable to conform to only a standard Gaussian. We want it to conform to a Gaussian mixture, which is a mixture of Gaussians. So what we do is actually we use another extra component, which is this one, PC given Z, which actually infers the cluster, which is which Gaussian mixture does this latent variable belongs to, so that you can pull them out into very different clusters. And during generation, you can use a lookup table such that you store means and variances for each Gaussian mixture, and you can sample from these distributions into a latent variable Z and to do the decoding. So the objective function is of twofold, since we can do what we call an unsupervised clustering within the latent space. So we can see that this supervised form actually is very similar to the vanilla VAE elbow function, which basically you just add in the term C when we have the labels. But when we don't have the labels, what we normally do is we do a marginalization, which is we sum up all possible clusters that we have, and we use the same elbow function here, but it is weighted. It is weighted by this QC given X, which is actually our clustering probability, because this term basically tells me which cluster should I assign to given this data point, right? So this is basically a marginalization where we don't have labels. And additionally, we add in a term, which is basically a KL divergence between your clustering probability and a prior. This prior is basically how you assume your clusters are being distributed. It's commonly a multi-normal distribution or a uniform distribution. It depends on how you define this prior. So yeah, for all of the details I covered above are actually also covered in last week's presentation in a more detailed manner. So yeah, if you guys are interested, please do refer to that presentation. What I would like to focus today is to extend from there to say what are the strengths of using LVMs for style-based music modeling, okay? So the first thing is that, the first strength is that inference and generation components are jointly trained, because it is an autoencoder. So we have an encoder component and a decoder component. So after training, the model is not only capable of controllable generation based on given features, but it is also capable of inference. So if we look at this, we have an encoder and a decoder. So after you train this model, the encoder itself can be used independently as a style feature extractor, which is often interesting because you are actually doing training the model such that it can both achieve generation and also analysis capabilities. Okay. And the second strength, which is arguably the most important motivation of why we use LVMs, is actually it allows interpolation. This is also the strength that distinguishes LVMs with probably simple conditioning, where we just concat the conditioning signals into probably before generation or before any neural networks. It is because we have the ability to interpolate within the learned latent space. So there are two examples. One is that we do intra-cluster traversal. The most familiar example will be music VAE, if you guys have heard of it. So basically what they do is that they encode all music segments, monophonic music segments, into a standard Gaussian latent space. And by interpolating this space, what you can do is you can morph one of the examples of the monophonic music into another in a very smooth way. And another thing is, if we extend it to a Gaussian mixture model, which in this case we have several Gaussian mixtures, what we can do is inter-cluster traversal. So from one class to another, what you can do is you can traverse through this path. For example, this is the distribution for trumpet, and this is for piano, like last week's example. So by traversing through this direction, what we can do is actually a style transfer. So you can kind of explore some states between here, which are the states which lie between the sound of a trumpet and the sound of a piano. And this allows us to achieve creative applications such as gradual style morphing or style transfer by itself. Okay. And okay. And the third strength is it allows extension of using semi-supervised learning, as we see just now on how we extend the VAE elbow into a Gaussian mixture model. It is the integration of unsupervised clustering with Gaussian mixture VAEs. And we can have two forms of objective function, which is supervised and unsupervised. And arguably, in the music domain, we often do not have enough high quality label data. For example, in my domain, which is emotion, because of all kinds of reasons, right? You can have annotation difficulties, you can have high variance in annotations due to subjectivity and so on. So semi-supervised learning can be a solution to this problem. Okay, and we can rely on this because LVMs is basically using what we call a generative approach, because LVM is trained to learn to reconstruct the output accurately. So the latent space itself, even if you don't use any labels to learn it, it should have captured some useful and reusable musical features, because the output itself, the model is trained to construct the output accurately. So the latent space itself must have captured some kind of useful and reusable musical features. And what we hope is that with only a little amount of supervisory signal or labels, we can further discriminate these musical features into some representations that we desire. So this is one of the strengths of using LVMs as well. And finally, it is the strength that it allows the application of feature disentanglement. This is also shown in last week's June's framework, where you can learn separate latent spaces such that each of them governs and controls one of the features that you want to control. And one of the way to constrain the latent space to contain the information that you want is to actually jointly train a classifier on top of this latent and value. So for example, if you want this latent space to encode timbre and this is pitch, then basically you jointly train a timbre classifier and pitch classifier here. So with feature disentanglement, we can, for example, if you have a piece, you want to model rhythm and note in very different spaces, you can do that using this approach. Okay, so the third thing I would like to review about is on controllability in latent spaces. So just now we talked about the application, which is the interpolation within the space, which it looks like in this diagram. So how do we ensure that the latent space can be controlled in our desired manner? For example, in this space, probably we don't know how these points are being distributed. So how do we ensure that, for example, I travel from this space to this space, and for example, this is a space of modeling rhythm density. How do I ensure this traversal goes from, for example, low density to high density? If you use previous methods, we can't really have this hard constraint within our training. But there are a lot of ways to do it. Within the image domain, there are actually a lot of papers there, but not many are being introduced into the music domain. So today I will talk about two methods, existing methods, which is using latent regularization, which they introduce control on the factors of music domains. Okay. So one of it is proposed by Gaetan Hadrias, which is called geodesic latent space regularization in the short form of GLSR. So the idea of this is, firstly, we have an attribute function. So we call it a G. So Y is the attribute and X is our music sample, okay? So G is our attribute function. So we have a function that transforms the music samples into the attributes. And we have a capital G. Basically, if you look at this term, capital G means you take in latent vector that you have, and it projects to this term, which is basically also the attribute function on the X, but this X comes from the reconstruction of Z. In very simple terms, it is applying the attribute function to the reconstruction output, okay? So if we have this function, then the regularization loss of this work is basically a log likelihood of the gradient of this function with respect to z. Okay, so what is the key idea behind this work is basically he wants to link the infinitesimal changes of z, which is because he used this differentiation, with the changes of g. In simple terms, how much you change in z should reflect in how much the change of your attributes in your reconstructed output. Okay, so this is why it's called geodesic, because it basically have a geodesic line in mathematical terms that hardly ties up z and the output attributes. Okay, so and it requires this differentiation to happen, because this differentiation basically encodes the gradient between your output attribute and your latent. Okay, so the formulation requires two things. One thing is that you need to have an explicit attribute function, and the second thing is that the function must be differentiable with respect to z, which the second one is more important. Okay, but for a lot of attributes, these two conditions may be hard to achieve, right? For example, if you have a rhythm density function, but the rhythm density function is often a counting function because you want to count the onsets and you divide by, for example, the length of the piece. So it's basically a counting function. Some attributes are basically argmax function, which you take the maximum argument and so on. These functions are actually non-differentiable with respect to z. And for this case, it will be hard to implement this approach because it requires it to be differentiable such that when you train it using backpropagation, this gradient can be backpropagated. But for some attributes, it will be hard, which you will need some level of approximation. Okay, so this is the first approach that we kind of reviewed. And the second approach is came out in last year by Pati et al. It's also a latent space regularization. So this is much simpler to implement. So what you do is basically you have a z of dimension d, which is a latent vector, but you just take one dimension out of it. So it's called z of the dimension of d. And y is similarly your attribute. So firstly, what you do is you compute the distance matrix. The distance matrix simply means within your training batch of samples, you calculate the pairwise distance of, for example, if this one is the pairwise distance of this value, z of d. Okay, and if it is the attributes, then you will calculate the distance matrix of these attributes. Okay, then what he does is that for these two distance matrix, for the first one, he take a tan h, and for the latter one, he take a sine function. So this, both of these constrain the domain down into a space of -1 to 1. Okay, and he take the mean square error of these two terms. Okay, sorry. So what is the key idea behind this regularization method is this one. So for xi and xj, which are two different music samples, okay? So if the attribute for the first sample is smaller than the second sample, this relation should also be encoded in your regularized latent dimension. So this relationship is being encoded. It is kind of a similar idea with the previous GLSR approach, but the thing is, this approach do not require you to do differentiation, and you don't need to calculate gradients. You just need to calculate the pairwise distance within the training batch. Okay, so it's simpler to implement. But as you can see, this this relationship is actually encoding what we call relative distance. Okay, so it is not encoding the actual distance. It is just encoding the relative distance between the elements. So what we can foresee is that some level of precision will be lost, right? So an example in my experiment is you can see these two diagrams. The top one is colored with the actual values of the attributes, and the bottom one is colored by the regularized value of the attributes, okay? So you can see that, okay, it does encode some kind of trend within this attribute, but you can see that the precision is lost, okay? The precision is lost because this objective function don't really cover the actual attribute values. It covers the relative distance only, okay? So you can see that some level of precision will be lost. Okay, so here I review these two techniques for latent space regularization. I believe there will be more works coming out and there'll be a lot of space to improve on this one, but these are the two options that we have at the moment. Okay, so after having providing these prerequisites, I would like to talk about the first work that I'm involved in, which is controllable audio synthesis or for piano performances. Okay. So for this one, the type of style model is basically performance style. So we are dealing with audio, we're dealing with how each piano performance is being interpreted, okay? But as we all know, performance style is a very vague concept and we don't really have any labels to directly manifest this quality, okay? Krishna, I see your question. I'll refer to the last one first. Probably I will address. I'll address the last one first for Krishna's question. Could you explain again what you meant by precision in latent space regularization? Okay, precision in my term means the actual values. So, for example, if for example in attributes you have, for example, 3 samples, one have an attribute value of 1, 2, 3, okay? So it is 1, 2, 3. But in Z, it doesn't really conserve the ratio of 1. So in the attribute example is 1, 2, 3, right? So the distance between the first and second is 1, and the distance between the second and third is also 1. So the distance between them, the ratio should be 1 by 1, okay? But okay. Yeah, I will continue explaining it. So, but the thing is, in your latent space, for Z, for the regularized dimension Z, you don't really, you can enforce, for example, a value of 0.1, 0.5, 0.6, okay? It is still conforming to this relation, but the actual ratio between the distance will be lost. This is the idea of what we call the precision is lost in this term, okay? Yeah, so thanks a lot for Krishna's question. I will address the last, second last question after the presentation. So sorry about that. Okay, coming back to audio synthesis for piano performance. So just now we talked about performance style is very vague, it's very hard to quantify, it's hard to label as well. So what we did is we take two what we call low-level performance features. One is articulation, which corresponds to staccato and legato. For those who are not familiar, staccato means it is more detached, and legato means it is more connected between the notes. And dynamics is basically loud and soft, okay? These are the two significant features that relate to the expressiveness in piano performances, okay? And so the dataset that we use is basically Maestro version 2, which is actually the Yamaha Piano E dataset, and they have pairing audio and MIDI. So how we pre-process it is for audio, we convert it to Mel spectrogram representations. And for the articulation and dynamics signals, what we do is we extract binary sequence labels for both. So it is sequence, so the length of the sequence is basically the number of time steps in your Mel spectrogram as well. Okay, so they are both paired up together. Okay, so how we get articulation information is that for that time step, if there is at least one note being held for that time step, then we set that time step articulation label to 1. So it's basically, if you are familiar with the notion of onsets and frames, we are taking the frame information here, okay? Then for dynamics, it is loud and soft. So what we do is basically we calculate the average velocity across all notes for a particular time step, t. And if the average velocity is greater than a threshold value, I found it to be at 70, then we assign it as 1, else it would be 0. So we try to extract these binary sequence labels for both articulation and dynamics as a supervisory signal. So now we look at the architecture. If you have looked at it, it is pretty similar to the framework presented last week by June. It is almost the same. Because it basically disentangles articulation and dynamics from a given piece, and we try to model them and conform it into a Gaussian mixture prior. So what we do is in the inference part, we will have an input Mel spectrogram, and we will model 2 latent space, one on articulation and one on dynamics. And we encode the sequence of latent vectors. Basically, sequence means it follows the time steps of your Mel spectrogram. And we encode for each time step 1 latent vector for both articulation and dynamics. And for each latent vector, it is further passed into the cluster inference component which you infer whether it is 0 or 1. So here it is basically a Gaussian mixture prior, okay, which we have an additional cluster component. And during generation, what we do is we feed in only the onset piano rule. Why we feed the onset piano rule instead of the full piano rule is we want to disregard frame and velocity information in the input, so that this information can be filled in by our latent vectors during the decoding, okay? So for this part, we use the latent vectors, the sequence of latent vectors for both articulation and dynamics. We concat them together, we pass in a global decoder, and we predict the MEL spectrogram. So for all encoders and decoders, we just use simple 2-layer by LSTMs to achieve this. And what we do is, at the final part, to invert this MEL spectrogram into audio, we use a Wavelo vocoder. Okay, so that would be an interesting thing is how these Z latent vectors come. So we have two sources, right? One is that you can infer from one of the pieces using this part to get it from here to here, okay? And this is actually a style transfer application. Another thing is you can actually traverse this latent space, right? Because you have Gaussian mixture, what you can do is you can do inter-cluster traversal. So you can have a gradual style morphing application here, okay? Then I'll cover these two applications later. So what I want to say is that for the objective function here, it is basically the same with the ones that I presented just now. It involves a reconstruction term, a regularization term, which is the KL divergence, and also a classification at this part, which you want to use your labels to supervisedly train your cluster inference model. Okay, so some of the applications, first one I mentioned just now is gradual style morphing. What you do is to get your latent articulation, what you do is you traverse from one of your staccato, 0 is staccato articulation, to legato. So this is basically interpolation from staccato to legato. And this is your, what you call your traversal vector, right? And it is traversed according to your time, with respect to time, yeah. So these are the 4 examples that you have. You can traverse articulation, you can traverse dynamics as well. So we have basically 4 scenarios. So you can see from staccato soft, it is quite soft and it is staccato. So you can see detached signals here and here. And when it goes to legato, it starts to connect more and more. So this is how you can see it from the spectrum. Okay. And the second application is actually performance style transfer, where given, for example, a more detached piece, I put the piano rules here for reference, so you can see that it's more detached. And the style piece, which is more of a romantic era style with more rubato and more legatos going on. And you can use this style and the onset piano of this piece to generate a new piece. So you can achieve a performance style transfer, okay? So enough talking here. What I want to show you is basically an example. I want to see, let me know if you guys can hear the sound. If not, please tell me in the chat. So I'm going to play one of the examples that I shown just now. This is the original piece. So feel free to tell me if you guys don't hear any sound, okay? Okay, thanks a lot, Lons. Thanks for telling me. Yeah, so this is the original one, more of a romantic era song. Yeah, so how we start to do the traversal, okay? So we start to listen to a staccato soft to legato loud. Sorry, let's start from the beginning. Okay, and staccato loud to legato soft. Sorry, now staccato loud to legato soft. legato soft to staccato loud. Okay, and the last one is legato loud to staccato soft. Okay, so this is the traversal results, and all of the audios are being inverted from spectrograms, MEL specs to Raven. How do you convert MEL spectrograms back to audio? We train a WaveGlow model. The WaveGlow model is trained based on the MEL spectrograms within the Mistral dataset. We use the ground truth MEL spectrograms and we invert it back into audio. And so basically we are using this WaveGlow model to do this vocoding. Yeah. So there are some other examples. The second example I want to show is on performance style transfer, which gives creative applications on this. So yeah, thanks Jun. This is a joint work with Jun actually. So Jun is handling the WaveGlow part. So he will be an expert on that. Okay, so for performance style transfer, it is basically that we have a content piece. You can see for this example, it is a Baroque piece if I'm not wrong. Okay, so it's a Baroque piece, and we use a Romantic era style piece too. Yeah, we extract the styles. So you can see for most of the parts, it is more legato and it is more rubato and so on. And so this is the result, which we use the style latents from style piece and to condition it on the content piece. So the Baroque piece, at first when I listened to it, it directly transformed into a Romantic era song, which actually can support more creative applications here because we can discover more creative and different types of interpretations for a lot of existing piano pieces. Yeah, this is the motivation and the applications supported behind this work. Okay, back to the slide. Can everyone see my slide, right? So let me continue on the second application, which is to learn to control high-level qualities via low-level features. Here I'll be talking in a more high level for this part, which is on the framework and the idea behind this application. Okay, so under this part, the type of style that we are modeling is actually a high-level semantic quality, such as arousal, emotion, mood, and so on, which is often very hard to quantify. Okay. And the motivation of using this, of having this, is basically that high-level musical qualities are abstract and subjective. Hence, obtaining labels for them often you need human annotations, right? For example, emotion and mood text and so on. However, we have two main obstacles that actually hinders us for training a good model. Okay, so the first one is that the amount of labels might not be enough because you know the annotation can be costly, right? So the amount of labels that you obtain may not be enough to train a model that generalizes well. If we just use those examples with labels and we train it in a supervised learning manner, okay, it may be not enough. And the second thing is that the labels could have high variance among raters. If you have more labels, then you can find it is more noisy. And when the data points are more noisy, it is very hard to train it, especially for emotion. Hopefully, if you guys have worked on emotion-related projects, I think this is one of the pain points that we often encounter. Okay, so the approach here is that why not we use a set of related low-level features, okay, to relate the qualities of the high-level feature. For example, an example that we have tried is actually to use rhythm density and note density, and we try to model arousal by controlling these two factors. Okay, of course there are a lot of related. There are more and more factors that are related to arousal, like for example dynamics, tempo, and so on. Yeah, but as a start, we experiment on these two factors. Okay, so the idea is that we want these low-level features to be controllable, right? So how do we make it controllable is we use disentangled latent spaces and we introduce latent regularization methods, like the two examples that I have presented just now. Okay, so this is how we can control these low-level features. And how are we going to relate these low-level features so that it can exhibit the qualities of the high-level features? So basically, you have a lot of controlling factors on these low-level features. How can you control them such that it exhibit a high-level feature? In simple terms, how you control rhythm density and note density in a way that it can be correlated to high and low arousal. The idea from here is to use Gaussian mixture VAEs, where your cluster refers to your high-level feature and your latent Z refers to your low-level feature. Okay, so this idea can be, or to say this framework, can be used for high-level features with discrete states and low-level features with continuous values. An example would be that we quantize arousal into high and low arousal, and we have continuous values on rhythm density and note density. Okay, so this is a more high-level introduction to this framework. Okay, so one of the examples I would like to share is if we look at this diagram. So we have the arousal clusters here for both rhythm density space, which is the top row, and the note density space for the bottom row. Okay, let's look at the rightmost column first. So the blue part is actually corresponding to low arousal, which is more calm and so on. And the orange cluster is actually high arousal, which is more exciting and happy and blah and so on. Yeah. So you can see that firstly, it is being separated into two mixture models, which thanks to GMVAEs, right? And the second column here is basically the regularized Z values with respect to rhythm density and note density, okay? So this is basically a higher rhythm density and this is lower rhythm density and so on. And for reference, I put in the density, the actual density values as well. So a few observations. Firstly, of course, the regularized values are, the regularized dimension is capturing the overall trend, but again, losing some level of precision. This is the first thing. And the second thing is more interesting is how we infer this to, how we correlate the high level features and the low level features, right? So you can see for low arousal, it actually corresponds to low rhythm density and actually a high note density, which you can see that it actually makes sense because for low arousal music, it is more chordal, which you have more chords, you have more sustaining notes. So you have a low rhythm density because you have more sustaining notes, and you have more chords, so you have a higher note density. Okay, these relationships are being inferred from a data set, so it is not being handcrafted because oftentimes people, the existing methods actually handcraft these relationships, but here we try to learn these from an existing data set. Okay, and in the opposite, for high arousal, it corresponds to high rhythm density, which you have a lot of running notes, arpeggios, and so on. And low note density, because it's running notes, they are single notes and it often does not exhibit a chordal structure. This is what we learn from the dataset we have. And we kind of see that this actually helps us to correlate high level and low level features together. So the good thing, what is the good thing about this is because oftentimes arousal is hard to quantify, and now we have a way to quantify it by using low level features. And the interesting thing is we can do inter-cluster traversal. from in the arousal space. So you can imagine from here to here, it is basically increasing the level of arousal. If you have two interpolations here, it is interpolating from low and higher, from low arousal to high arousal within the space of rhythm density and note density. Okay, so these are some of the output examples. In piano rolls, I don't really have the audios at the moment, so sorry. So yeah, so for example, this is a high arousal song. You can see more, what you call it, running notes, and it's more choppy. And when it goes to low arousal, it becomes more chordal. And it is the opposite in this case, okay? Yep. So finally, we come to a conclusion and future work part. So there are some takeaways that I hope that I am able to convey to you guys about this presentation. The first one is the motivation of using LVMs for style-based modeling is basically it allows controllability. And the controllability can be done in a more meaningful, lower dimension manifold latent space. And secondly, the good thing is that LVM supports semi-supervised learning, and which is valuable because we often do not have a lot of high quality labels. And thirdly, for high level abstract musical qualities, we can learn several disentangled space, which corresponds them to low level features. It actually exhibits in both of the works. Like for performance features, we also use low level features such as articulation and dynamics. For arousal, we use rhythm density and note density, okay? So we try to use disentangled spaces, control them in a constrained manner so that it exhibits the high level quality. And the future work for both of these will be to expand these frameworks to model more types of style features and to produce musical pieces of a longer duration. This comes to the end of my presentation. Thanks a lot. I will go back to address one question that I have seen being raised by Krishna. The in-between states in latent space need not be perceptually meaningful, right? Yes, it need not be if it is being trained in a non-constrained manner. But as I mentioned just now, we sometimes want it to be perceptually meaningful. For example, when we are doing interpolation, or for example, in my second application where you want to control some of the factors in a more constrained and controlled manner, you don't want holes within the unlabeled parts. Like we often talk about a problem, which is the holes, which are the, the holes within your latent space, which makes it not so smooth, and it is therefore not perceptually meaningful, right? But oftentimes we want it to be, so which is why latent regularization is there. Yeah. Are there any more questions that I would be able to address? I will try my best to.
Hi, Hao. Thanks for the great presentation.
Okay.
I was wondering, since I think Raven asked a question about the conversion of the MEL spectrograms, that's sort of a limitation to the usability of the system because you always have these artifacts when you convert, right? Does the architecture, you think it would perform well with some wave architecture?
Yeah, good one. Good question. So it is possible, but one thing is that if we model directly on audio, we need to have a very high resolution space to model it, because in MEL spectrograms we can use MEL bins, and we can for example use a how to say it? We can use a shorter length to model, for example, a 20-second audio. But if we do it on a wave domain, then you have a higher resolution that you need to model. So that is one challenge if we model directly on audio. And the other thing is, indeed, there are artifacts in the current work for our audio synthesis, but we do believe that this is because of wave glow. So there are a lot of vocoders that have been developed. One of it, the most well-known one is WaveNet, but of course, WaveNet trains for a very long time. And of course, there are WaveGlow, there are WaveRNN, and there are a lot of vocoders that we can venture into it. Yeah. So I believe the WaveGlow part can be improved, because if we look back into the paper of Wave to MIDI to Wave by Google Magenta, they actually achieved quite a good result. But I don't know how long they've been trained for. So that's another thing. Yeah. So I believe that if we focus on improving the vocoding part, that it will be okay. And what's more, a lot of vocoders have been used for text-to-speech, and they are performing very well. So we are trying to incorporate that. How does WaveGlow compare to WaveNet? Question by Chitralekha Gupta. In our current work, we don't really try WaveNet yet. And for now, we have only tried WaveGlow. But there is a literature that actually compare across all vocoders. If June, you are here, you can probably help to attach that. And it compares across several vocoders, and I believe WaveGlow is the one that they claim to be the best. Yeah, but of course, when we are using one of the implementations of WaveGlow on GitHub, and we do run into some problems with it. For example, some of the frequencies are being hidden, and some of the artifacts are there. But I think this part can be improved, and the output quality will be improved. Yes.
Oh, I've got a question.
Yes. Hi, Lawrence. Yes.
So I wasn't clear on why you discretized the dynamics and articulation to be one of two values only. Why not let those be continuous to capture that whole range?
Sure. So why we want to use discretization is because one of the reasons is that multimodal representation can be more controllable. This is one of the things, because if we have 0 and 1s here, they are two multimodal latent space. So it is a multimodal representation. And we can easily say that this is a low arousal cluster and this is a high arousal cluster. Of course, the other way can be to regularize it. For example, to regularize on the Z values. But what we try to claim is that using discretization and Gaussian mixture priors can introduce a multimodal prior into it. And multimodal priors are often more controllable in terms of interpolation. Yeah.
And then you found that you didn't have too big of holes between the two clusters then in those cases where
yes
we often find that we get nonsense between the clusters where we didn't have training vectors. So that's why I'm asking these questions.
Sure.
But you find that you can smoothly morph between regions that where you didn't really sample from in that case.
Yes. So for my case, I find that from the examples that I have synthesized, it sounds quite smooth at the moment. Yeah. But another thing, one of the benefits that I think of using binary signals is that because binary signals are more easy to obtain. This is one of the motivations that I use binary signals, because, for example, in terms of articulation, it is hard to quantify it into a continuous value, such that But in my case, we can just use 0 and 1s, and we let the model to explore the intermediate states within this 0 and 1. And in my work, it seems like these intermediate states kind of work well. Yeah.
Yeah, just to pursue that just a little further, it almost seems like you're giving it bad data, because you're gonna train it as if the articulation is binary when it's not, when the data itself is not. So it almost seems like it's like mislabeling in a way.
What do you mean by mislabeling in this case?
Well, that you're force fitting data that might have an articulation that's in between legato and staccato. And you're calling it one or the other.
But this actually happens because, for example, if I only use, for example, 0 and 1s, I don't model the intermediate states. When we are when we are playing across time, which is probably this piece starts with legato but ends in staccato, it can flow smoothly. It can morph smoothly from legato to staccato, which is why we want to explore the intermediate spaces. Because with this, then we have when we do style morphing with respect to time, then it can be morphed in a more smoother manner. Yeah.
Thank you.
Okay. Thanks a lot, Lawrence. Yeah. But a question by Ray: can you elaborate the benefit of adding the LSR, which I believe is latent space regularization, you talk about the ratio between Z and output. Are there other benefits? The main reason for adding latent space regularization is because we want to control it. So, and want to control it in a manner that we want. So let me get back to that slide if I can. Yeah, so for example, in this, is it this slide? Let me see. Okay, probably this slide is the best to explain. So if we don't do latent regularization, within the training, we don't really have a single dimension or a single variable that we can linearly map your dimension, your latent dimension, to the attributes that you want to model. For example, today you want to change across time from 0 to 1. If we don't have a latent dimension regularized, we can't really change that because within your training, you didn't enforce this hard constraint. So basically, latent space regularization says that you impose this hard constraint to say that one of your dimensions must be mapped to the change of the final output. So the intuition of using LSR is basically for controllability. You want to control that dimension. And yeah, and to clarify the ratio, I mentioned about the ratio between Z and the output is actually to discuss about the loss of precision with Krishna, if I'm not wrong. Yeah. So if we are using Patti et al.'s method, then some level of precision will be lost.
I don't want to. I have another question, but I don't want to.
Sure.
Someone else has one. Okay, so in some of the visual style and work, as like style transfer, and also with some of the speech stuff, when you extract style and put it back together again, the style and the content interact with each other, right? So there's a the swirls of Starry Night will show up around points of light on your reconstruction when you're using different content. Here, it looks like you're extracting these style features and then superimposing them. In other words, when you provide a style vector, it's not going to be responsive to what the content is doing. It's going to make things more staccato, or it's going to make things more legato, but it's not going to make the staccato dependent on the pitch of the notes, say. Is that correct? Are you're pulling them together, you're pulling them apart so that like you take the dynamic features of the romantic piece and you superimpose them based on the time when they occurred in one piece and put them in the same place in time on the other piece, but it's not going to be sensitive to the content in anything other than when and where the notes start, because that is your content. Is that correct?
Sure. Yeah, I think it's correct, and I think in this context, we want it to be not sensitive to pitch, for example, or to factors other than the attributes that we are modeling. For example, we want articulation to only be governing articulation factors, and we want dynamics to only govern what we call our dynamic factors. So it is disentangled in this case. And I believe you are right to say that in terms of this context, basically you are superimposing different disentangled representations together and adding up on the pitch and to to generate the output. Yes, but I think this is probably a desired objective that we want to achieve, because we want to with better disentanglement between these parts, then we can control them more better independently. So probably this is the reason why we want them to be separate with each other. Yeah.
Okay.
One more question added up by Ray. So that is better than exploring the latent space and finding an attribute vector approach. What do you mean by an attribute vector approach? Do you mind elaborate more on that? And thanks, June, for explaining the difference with WaveGlue and WaveNet. A latent vector for pitch contour. Yes, so when you train it, for example, let's say you have a vanilla VAE and you have a latent space within which you try to encode a pitch. but you don't know how this latent space grows or looks like, right? You don't know where is the higher ones, you don't know where is the lower ones. You can have a very complicated surface where you have high and low and high and low and high and low and so on. But you probably want it to be just unidirection where you can traverse from low to high. Yeah, do you get the idea? So if you don't do regularization, you can't ensure that your latent space is smooth, or you can't ensure that your latent space is being distributed in the direction that you want it to be. So this is why we use latent regularization, is to impose a high level of controllability, and you ensure that the latent space grows, the latent space looks like how you want it to be. Yeah. Okay. Any observations on using, wow, a lot of questions. Any observations or comments of using a standard log MEL spectrogram, log MEC should be a MEL spectrogram, right, over a MEL spectrogram from Krishna. Log magnitude spectrogram over a MEL spectrogram. For this work, we don't really experiment on log magnitude spectrogram yet. The reasons why we directly choose MEL spectrogram is because of the assumption that, not the assumption, for the observation that it is more closer to human perception, which is why we just directly use MEL spectrogram. We haven't tried that, but thanks for that. By Raven, in one of your slides, you mentioned that you also added classifiers to regularize the latent space. I wonder what is the size of your input. Okay, let me get back to the slide. Yes, Raven, you are right. The MEL spectrum is already in log magnitude, but we don't really, to address Krishna's question, we haven't tried MEL with non-MEL comparisons. Yeah, I believe it is this slide that you are mentioning, Raven. For this slide, it is more of a high-level description. So I wonder what is the size of your input number of time steps. For the audio, the audio synthesis one, it is 20 seconds of audio. So when I convert it to MEL specs with, if I'm not wrong, 1024, 2048 hops, then it will be, I think, 650 something time steps for the audio synthesis one. For the latter one, which is the symbolic one, the arousal one, it is basically taking only 100 tokens, and the tokens is from Music Transformer, which is the conversion between from a from the MIDI files into event-based representation by the Google Magenta transformation. So it is tokens. It is basically tokens. So I take 100 tokens. Yeah. Okay. So a follow-up question by the Raven. Then the classifier might have a lot to classify since many events happen in, for example, 20s. So the place that I use classifiers is, I think, here only in this part, which the way that I do it is I do I use a additional LSTM to use the final representation, and I use that to predict the output. So my classifier is basically a sequence model, which I take in a sequence and output a label. Yeah. Yeah.
Right.
Thanks, Rigo. Yeah.
Thanks a lot for presenting How. Very much enjoyed it. We can stay online a little bit longer in case there are more questions, but in any case, I just want to thank you. And if there's no more questions, we can slowly end the meeting.
Sure. Thanks a lot. Thanks everyone for joining. Yeah, so there's a good additional question by Ray. How do you explain that the high arousal correlates with the low note density? Yeah, so if I'm looking at my slides, Ray, so this is the slide. Actually, when I'm sharing the screen, the group chat is up here also, right? I'm not sure, but never mind, it's okay. So if you are looking at the slides, so if you look at these two diagrams, so for example, this is high arousal when we are talking of it. Then these are, so each of the diagrams are the same. It is clustered according to arousal, but I colored it in different terms. This is colored in terms of regularized Z values, where the darker means the higher note density, the darker the higher rhythm density. So you can see that this is the high arousal cluster, and this is of darker color, which corresponds to higher rhythm density. And this is how we infer it, which is by comparing these two columns, and we can find if we learn the qualities in a reasonable manner. I mean, the high arousal correlates with low note density, right? Yes, exactly. So yes. Oh, how do you explain that high arousal correlates to low note density? Yeah. Okay. The data set I'm using, you know that is VG-MIDI. So if you look at VG-MIDI data set, most of it with high arousal, it is basically arpeggios running notes, which are very fast running notes, which you don't really have a chordal structure. It is often playing one note at a time. So which is why it is low note density.